Hi, welcome to a podcast on percent composition, empirical formulas, and molecular formulas. Today we're going to learn how these tie into moles. If you need help with moles, you can go back to the Mole Problems podcast. And if you've seen this picture, this couple is moving some boxes. They're mailing them some things to their relatives. And let's say in the boxes on one of the side, they have one computer and two mittens. So there's 3 total items. Now, how would they, if they went to the post office, how would they be charged? They wouldn't be charged by 1, 2, 3 different items. In other words, this mitten right here is not 1/3 of the whole shipping fee by mass. There's 1 out of 3 items. 1 is a mitten and 3 total items. 1 is a mitten and there's 3 total items. And 1 is a computer and there's 3 total items. But that's not how the post office charges you. Goodness no. They charge you by how much it weighs. So that's exactly how percent composition is tallied up. You figure out what the part is over the whole by mass times 100. If you just did this part over the whole, you'd have a ratio. To actually find percentage, you need to do part by mass over the whole thing by mass over 100. And I already know that out of this box, if they were mailing a computer and 2 mittens, that the computer would definitely have more mass. It would take the largest percentage of it. So let's look at this. Okay, so a percent composition, again, is a mathematical method that's used to determine the percent of each element by mass, just like going to the post office in a compound. And so if you look, this is part over the whole times 100 equals percent composition. So let's do this for a formula. You know this formula is sodium chloride. So I know sodium's mass, and let me actually use a different color so you can keep track of it a little better. Okay, let's use blue. Sodium's mass on the periodic table is 22.99 grams, and chlorine's mass is 35.45 grams. And if you add these two together, my total mass of my whole compound is 58.44 grams. Now, how would I figure out the percent composition of sodium and the percent composition of chlorine? And you would be right by saying there's 1 sodium and 1 chlorine, but sodium, just like the computer and the mittens, is not an equal partner or equal mass to chlorine. So the way you do this is you take the part that's sodium, 22.99 grams. That's how much sodium weighs in this compound. And you take getting ahead of myself. Sorry, I got distracted. So you take 58.44 grams, that's the whole thing, and then you multiply that by 100. And when you do your math, which I'll do in a minute, that is the percent of sodium in this total compound. Now if you look, in chlorine, what do I have? Chlorine's heavier, isn't it? So it's going to take up more percentage-wise of my part over my whole. So this is how many grams of chlorine I have. This is how many grams of sodium chloride. This is how many grams of sodium, and this is how many grams of sodium chloride. Part over the whole times 100. Again, if I just left the fraction, I would have a ratio. So when I do my math, I'm going to end up with 39.34% sodium. And when I do my math, I'm going to end up with 60.66 grams of chlorine. And if you notice, these two numbers add up to equal 100%. Let's try a harder one. So here I have aluminum hydroxide. Again, we're doing percent composition. The problem would say something like, find the percent aluminum in aluminum hydroxide, or the percent oxygen. So aluminum is Al. It's a positive 3 charge. And my polyatomic ion's hydroxide, it's a -1 charge. They're not going to play ball equally, are they? So throwing 3, catching 1, I'm going to have to write a 3 down here because I need 3 of these to play ball with 1 aluminum. All right, now how do I find out my percent composition by mass of each of these? Well, a little different. I have 3 different elements. I have aluminum, I have oxygen, and I have hydrogen. Now, I need to figure out how much aluminum I have. I have 1 aluminum, don't I? 1 here. And I have 1 here, but I have 3 oxygens. And I have 1 here, but I have 3 hydrogens. So 3 times hydrogen's mass, 3 times aluminum's mass, and by oxygen's mass, and 1 times aluminum's mass. So in the periodic table, under aluminum's mass, it's 26.98 grams. Under oxygen, I have 16, and that's going to be a total of 48 grams for oxygen, because 3 times 16 is 48. And 3 times 1.01 grams in the periodic table is 3.03 grams for hydrogen. So now, before I go any further, I need to add all these up to get my total, which is your gram formula mass, isn't it? 78.01 grams is the whole thing. That's the whole compound. So how do I do my math now? I do my math by saying 26, let's close this, there you go, 0.98 grams of aluminum over 78.01 grams total equals times 100 equals 34.59%. That's aluminum. For oxygen, I'm going to take 48 grams of oxygen over 78.01 grams. That's the mass of the total compound, times 100, and that's going to give me 61.53%, and that's oxygen. Okay? And how do I do my last part? Well, it takes 3.03 grams of hydrogen over 78.01 grams for my total, times 100, and that's going to give me a percentage of 3.88%. And that actually makes sense, doesn't it? Because if you look, my total mass is 78.01, and my hydrogen is only 3.03%. That's a tiny percent. That's why it matches up with that 3.88. Okay, what's my heaviest? My heaviest element total is oxygen at 48 grams out of 78, and that's why my percentage of oxygen is the most, 61.53%. So that's how you do percent composition. It's pretty straightforward. Part over the whole times 100. So now let's move to empirical formula. An empirical formula is the simplest whole number ratio. So if I told you that I had a compound like this, C6H12O6, glucose, is that the simplest whole number ratio, the empirical formula? In other words, can you simplify that? If you look, I can take a 6 out and make that CH2O, or one of these for every 2 of these and 1 of those. Doesn't that match up to equal this compound? Now, this right here is called the empirical formula for glucose. It tells me the simplest formula, the simplest ratio, but it doesn't tell me exactly if this is all I know. In other words, I can't tell you what compound I have. Could my compound, if my empirical formula is CH2O, could it be glucose? Sure it could. Why? Because if you multiply this by 6, you get C6H12O6. What would happen if I multiplied it by 4? Couldn't I also have C4H8O4? So these are possible formulas, possible molecular formulas, but we're looking at an empirical formula, the simplest whole number ratio. And that empirical formula is the same for both of these. Now, let me ask you a question. Is this true? If this is my empirical formula, is this a possible compound that could fit? C5H14O2. Well, let's look and see. If that's true, then I'd be multiplying my carbon by 5, which would make this CH2O H2O. We'll make this 1 times 5, so that works. So it works for carbon. What's 2 times 5? It's 10. There's not a 10 here, is there? That's a 14. So this empirical formula cannot match up with this compound. It can only match up with these two because there's a multiplier that you can multiply this CH2O by to get the new compound, the actual compound. So again, a simplest whole number ratio is a simple formula for a compound. Now question, if I have water, H2O, that is what water is, isn't it? That's the molecule of water. But guess what? It's also the empirical formula. Same thing for carbon dioxide. That's the molecule. It's also the empirical formula. It's a simplest whole number ratio. You can't go any smaller. But what about for glucose? C6H12O6. Can you simplify that down? Yes, you can. To CH2O. This is not what it really is, but it's the simplest whole number ratio. So, now I'm going to give you a poem. You need to write this down, and I got this from the Journal of Chem Ed many years ago. I kind of modified it a little bit. And this is the directions. It tells us to do percent to grams, grams to moles, divide by small, then round to a whole. So let's use this poem to help us out. And the reason, by the way, why I can do this percent to grams part is if I have a sample of a compound, I could have a tiny spoonful, I could have 100 grams full, or I could have a huge swimming pool full. And in each case, if I have a total, I have 100% if I have everything in the spoon. I have 100% if I have everything in the cup filled up, right, everything in the spoon. And I have 100% if I have this whole pool filled up. But how convenient if I have 100 grams and I have 100%. If I have all of my 100 grams, and that means that 100 grams equaling 100%, that means 1 gram equals 1%. That's why this step works. If you understand that right now, that's good. If you don't, then don't worry about it for right now, and we'll just move on and use this poem to help us solve problems, and we'll come back to that later. So, what do I need? Percent to grams. That means I'm physically going to take this word percent right here, this symbol. I'm actually going to change 75 grams of carbon and 25 grams of hydrogen. So that's this step. Right? Just did that. Check. What's my next step? To change grams to moles. Well, how do I do that? That's my mole map. 1 mole here. Over here I have grams, right? My mass in grams. What do we pass by to get to that? The periodic table. So I have carbon here and hydrogen here. So let me turn the page so I have way more room to work here, right? And I change this to grams. I'm going to use my train tracks. I'm going to put the word grams down here, put the word mole up top. On my mole map I have 1 mole in the mole hole, and on my periodic table I have 12.01 grams of carbon. Okay, so I already changed percent to grams. Now I'm in the process of changing grams to moles. I put grams for hydrogen down here, moles up top, 1 mole here. This is 1.01 grams on the periodic table. And I'm going to go ahead, and my answer is 6.24 moles of carbon. And over here, it's 24.75 moles of hydrogen. So that's step 1 and 2. My next step, what's it say to do? My next step, it says divide by small. That means you look at both of these numbers, the 6.24 and the 24.75, and you ask yourself which one's the smallest. Well, it's 6.24. So I'm going to divide both of these by 6.24. That gives me the answer of 1 for carbon and the answer of 3.97, which I'm going to go ahead and just say that's 4 for hydrogen. So if you look, what order did they give this to me in? They gave me the carbon first and the hydrogen second. So that's what I'm going to do. I'm going to write the carbon first and the hydrogen second. And these numbers right here are the numbers that correspond to the subscripts. So it's C1H4 or just CH4. And that is my empirical formula. We're not going to do this step right now. I have a whole other podcast that we'll do for that step. But for right now, we're just going to do simple empirical formulas. Now question, is that what this molecule really is? I don't know. It's a simplest whole number ratio. It could be CH4. It could be C2H8. It could be C3H12. But it can't be C9H55 because this does not match the empirical formula. So again, an empirical formula is real good for telling you what it could be and what it can't be. But for right now, that's not what they're asking us. They're asking us simply to find the empirical formula. So the next step is to find the molecular formula, to find out the formula of a molecule, what it actually is. So, what are they asking us in this question? The empirical formula of a compound is CH4. Hey, that's what we just did. So we know the empirical formula, the simplest whole number ratio. If the molar mass is 64 grams per mole, then what is the molecular formula? The molecular formula's mass is 64 grams per mole. You know that. That's what they're telling you here. And so whenever you see a problem like this, what is the molecular formula? You don't know that, do you? Okay? You're going to use this equation here. And you're just going to say me. And M is the molecular mass. And E is the empirical mass. And guess what? They always give this top number to you. Always. So if I come down here and write me, that means this 64 grams per mole is the mass of what my compound really is. Do I know what it is yet? No, I don't. But it really, truly, whatever it really is, has a mass of 64 grams per mole. You know the empirical formula. It's CH4. What's the mass of CH4? Well, let's write this over here. And this is 12.01. And this is 1.01, but there's 4 of them. So when I add that up, I get 12.01 plus 4.04, or I get a mass of 16.05. That's what this adds up to equal, 16.05 grams per mole. That's the mass of my CH4. Now if you look, the mass of what you have in an empirical formula is smaller. Isn't this smaller than this? So that tells me the mass of what it really is heavier than my empirical formula. So if you do your math and you divide, you are going to get 3.98. Well, that's darn close to 4, so we're just going to call it 4. And what does that mean? That means that my compound, CH4, that empirical formula, is 4 times lighter than my actual molecule, or my actual molecule is 4 times heavier. So I'm going to take this CH4 and multiply it by 4, and I'm going to have C4H16. And that is my molecular formula. That's what it actually is. And that makes sense if you look, because my molecular formula is 4 times heavier than my empirical formula. So that's the 4. And if you look, remember when we did glucose, we took a 6 out. What would you have to do to this compound right here to simplify it? Well, you take out a 4, and you would end up with CH4. Okay? One last problem. And this problem is a molecular formula problem. Because if you look at it, it goes, tells you some information, la la la, and what's it ask you? Oh, what is a molecular formula? That's your question. You have lots of information here. So what's a molecular formula? Oh, I know. That brings to mind that I should be doing me, right? And they give me a number here, 98.96. Ooh, that's this number up here, isn't it? 98.96 grams per mole. I don't know my empirical mass though. And guess what? They don't tell me the empirical formula. They're not very nice. They don't say, find the molecular formula, but they do give you this information. What's this information tell you to do? Well, it tells you to do a poem. What's that poem? Percent to grams, grams to moles. Divide by small, then round to a whole. They're trying to trick you. You need to find the empirical formula first. So let's go ahead and do that. Remember the process, and if you would like to turn this off and then look at the solution after, you can. So I'm going to physically take all these and change these to the word grams. Because remember, we're going to assume we have 100 grams. That makes each percent equal to a gram. So I just did this first step, percent to grams. Okay, so I come down here and I write 71.65 grams of chlorine, 24.27 grams of carbon, and 4.07 grams of hydrogen. That's my first step. What's my next step? It's to change grams to moles. So I'm going to use my mole map. And in hydrogen's box on the periodic table, there's 1.01, and I'm putting grams down there, and moles up top, there's 1 mole, so I'll use my periodic table. Grams down here, moles up top, 1 mole in the mole hole, 12.01 grams on the periodic table. Grams down here to cancel, moles up top, because that's where I need to go, 1 mole in the mole hole, and this is 35.45 grams. Now, on my calculator, I should get 2.021, or 2.02, and that's for chlorine, isn't it? Okay. If you can write moles of chlorine, you can. And then I get 2.021 or 2.02 here. Moles of carbon. Right, that's carbon over here. And then I have hydrogen, and hydrogen's 4.04. Now again, if you look, they give you the compound in order. See that? So over to the side here, I'm going to write ClCH. And I'm looking for little numbers. Even though this says molecular formula, I'm not looking for molecular formula first. I need to find the empirical formula. Because if I don't know the empirical formula, I cannot find the molecular formula. So, what's my next step? My next step is to divide by small. So the smallest out of these sure looks like it's 2.02. So I'm going to divide 2.02 into all these. And I get 1, 1, and 2. And so that's what I come and put over here. 1, 1, and 2. So it's ClCH2. And that's my empirical formula. Right there. Now, that takes me on my way to doing my molecular formula. So how am I going to do that? Well, let's go back to our word problem. In our word problem, we've done this step, right? That's ClCH2. So now this problem that I've done that is exactly like the problem we did over here, isn't it? We don't know the molecular formula, but we do know the empirical formula. So now we need to look at this section of my problem right here. Okay? Since I now have my empirical formula. So let's go over here. And if I know the molar mass, oh look, they give that to me. That's the M in me. Okay? My empirical formula again was ClCH2 from the page before. All right, remember back here? ClCH2. So what's that mean? Let's add this up. Chlorine is 35.45 grams. Carbon is 12.01. And hydrogen is 1.01, but there's 2 of them. So you add all these numbers up. And then that's going to get you 49.48 grams. That's the mass of my empirical formula. That's the mass of my molar mass of my actual molecular formula. So what's the molecular formula? Well, you divide these into each other and you get 2. So what does that mean? That means you take Cl, CH2, and you multiply it by 2, because what you really have is twice as heavy as your empirical formula. So your answer should be Cl2, C2H4. So if you'd like to replay any of this, you can. If not, I've given you all the information you need. You can go back and you can study the molar podcast, and you can look at this podcast, and that's going to be your test. So good luck studying, and I'll see you soon.